Okay, so we are in chapter 2, section 5. We're going to talk about nuclear equations and radioactive decay. So we learned what are the different types of radioactive decay last time. Now we're going to show how to write that in an equation. So if you start just with the words, uranium decays into thorium with the emission of an alpha particle. So even if I wasn't given any of the stuff that you see, like you already have the answer up there, but what would you do? You go find uranium on the periodic table. Uranium is a U. And so you would look for number 92. So 92 is our number of protons, right? So we're told, well, usually we would be told uranium-238 decays into thorium, right? And you would have to be told thorium-234, okay, with the emission of an alpha particle. So I'm told that's uranium-238, so I know this is my protons plus my neutrons. And it decays into thorium. So I go on the periodic table, I find that thorium has 90 protons, right? And I also know that an alpha particle is a helium nucleus. So it has 2 protons, 2 neutrons. So I can put a 2 for the protons and I can put a 4 for the mass number because I know 2 protons, 2 neutrons is a 4. So basically all you have to worry about is you have to make sure that the numbers on top add up, right? Okay, so on the left side of the equation, I have 238 for a mass number. It has to equal the number on the other side. So I have 234 and I have 4. Do they equal? Yes. So 234 plus 4 is 238. So 238 does equal 238. That's how we make sure that our equation is balanced in this case, right? So now we also need to check our atomic numbers. So here are our atomic numbers we got off the periodic table, and we know from our definition of a helium particle. So we know on the reactant side, we had 92. And we want to know, does that equal the products? So we have 90 protons in thorium, and we have 2 in the alpha particle. So 92 does equal 92. So that's how we know that it's balanced. So our atomic number in the reactants must equal the atomic number in the product. Mass number in the reactant must equal to the mass number in the product. So you have to remember in this that our element symbol, so here we went from a uranium to a thorium, right? Our element symbol is changing because our number of protons changed. We started here with 92 and we ended up with 90. Well, that's telling me that I have to have something that took those 2 protons, and that's that alpha particle. So if you change the number of protons, you're getting a different nucleus. That's a different atom. And so that's radiation. So just make sure that your numbers are balanced. So we'll do a bunch of these examples in a minute. So first things first, what do? Go write the symbol notation for the radioisotope. So remember we said that was uranium, what do we have? Uranium-238, right? So you want to go and write the symbol for that. Then put the ionizing radiation in a product. So it's going to change, and when it changes, it's going to release, in this case, we were told, an alpha particle, right? So if we do that, we're going to have to make something new. And I guess I really should have written this as, right, 238 uranium, and we had 92, right? Okay, so let me rewrite 42He. Okay, so now place the ionizing radiation on the product. We did that. Determine the missing product radioisotope. How are you going to figure that out? Well, I know that if I need to get a total of 92, this has to be 90 here. So then you can go look on the periodic table and you say, okay, which element has 90 protons? That's thorium. Then you can determine the mass number by looking here, 238. What plus 4 is 238? 234, okay? So just remember to check your mass numbers and atomic numbers on either side. So we'll do a bunch of those in a minute. All right, so different kinds of decay. In beta decay, you got to remember that you release a high energy electron from the nucleus, and a neutron becomes a proton. Oh, what happened to my symbols? Hang on. All right, so I got my things back. Now, we did alpha decay. So now we're going to do beta and positron and gamma. So in beta decay, we have a high energy electron emitted from the nucleus, and our neutron becomes a proton. And I'm going to do an example of that in just a minute. If you do a positron, it's going to be super similar to beta, except that the charges are different. Because a positron's positive, beta is an electron, so an electron's negative. So remember, this is positive, this is negative. Gamma decay. Gamma decay, remember, is energy only. So when you look at that, this is the easiest one to do completely, because both your mass number and your atomic number are 0. So it's not going to change the atomic number, not going to change the mass number. But by emitting a gamma ray, the element becomes stable. So this is an example of radioactive titanium. And they use this one a whole lot in medical uses because 96-97% of all the radiation decays in less than 24 hours. So if you put it into a patient's body, you can do the imaging, and then it doesn't hang out for very long, and then it clears the person's system. So they're not going to have radiation sitting inside of them for a really long period of time, which is what you really want with radiation that you use in the clinical setting. So although we do find some in nature, some of these radioactive isotopes, most of them are made in the lab. And so most of them are made by bombarding relatively stable isotopes with either alpha particles, protons, or neutrons. So here's an example of radiating an element with a neutron. And this is something that's really common in order to produce what you want. So this is molybdenum. And if we take molybdenum and we give it one more neutron, right? Now we go from molybdenum 98 to molybdenum 99. But what's really cool about molybdenum 99 is that it is actually going to decay into this right here, this titanium 99. And this is the metastable one that we want to use for the clinical setting. So this is something that we can create in a lab and then have a nice stock of this radioactive material to use in diagnoses and things like that. Okay, so we're going to stop there and we're going to go here to here. Okay, so this is what I want to do. Use the table provided and what type of ionizing radiation is produced in the nuclear equation. So here's our nuclear equation. What kind of radiation is produced? Well, I'm going to look right here, and I see that this matches an alpha particle. So this is alpha. So this is an alpha particle. So you can abbreviate that also with the symbol. Either one's fine. Use the nuclear equation above. Compare the following reactants versus the products. Answer as the same, more in products or more in reactants. So what happened to the total number of protons? So let's do reactants, products, and then we'll do our answer, just to make this a little bit easier, right? Okay, so number of protons, number of neutrons. So what happened to our number of protons? Here's our number of protons, 92 and 90, right? And if we look, we have 2 more protons, ooh, see if I can show it, inside of our alpha particle. So what happened to our protons? Well, in the reactants, we had 92. In the products, we had 90 plus 2 to give us 92. So guess what? We have the same. How about our number of neutrons? We know that our number of neutrons is our mass number. So here's our mass number, okay? So it's our mass number 238, that's our reactant, minus the number of protons, so minus 92, which should give us 146. Okay, now let's look at our product. Our product, we're gonna have to do two, let's see if I can move this down, two little math things, right? So we have 234 minus 90, and we have 4 minus 2. So we have 2 here, and then we have 144. So we add those together, and we get 146. So look, 146, 146, these are the same. And then our total mass number, let's see, 238, that's the highlighted yellow, 238. Then we have 234 and 4, so that gives us 238, and it is the same. So this is why we have to balance our nuclear equations, because we have to end up with the same number of protons, same number of neutrons, and same mass number, because we can't create or destroy anything, right? Okay, balance the mass numbers and the atomic numbers and write the correct atomic symbol to complete the following equation by filling in the blanks. Okay, what I want you to see right away is this symbol right here. This tells you that is a particular kind of radiation. So this is beta decay. In beta decay, what happens? You have to go back and remember this. In beta decay, a high energy electron is emitted, and don't forget, and a neutron becomes a proton. Okay, so if we remember that, we're going to get this right. Okay, so we have iodine 131. We have 53 protons. So what happens? We have a neutron that becomes a proton. So we have to fill this in with an element, right, that has a different number of protons. So 53, right, is equal to some number plus a -1. So 53 must equal to 54 plus a -1, right? Plus a -1 is just like saying -1. So 54 minus 1 is equal to 53, okay? So we know that our element is going to have 54 protons. So go look on the periodic table. Go and find, pause it, go and find what element has 54 protons. If you went and paused, xenon has 54. Okay, now what we also notice is if we look at our mass number, right, our mass numbers have to equal. Well, there's no mass here that's being emitted. It's just a high energy electron. So our mass number is actually not going to change. So our mass number is still going to be 131. And I couldn't fit that. That whole thing is supposed to fit in that little bitty old blank. But I can't do that. So that's your answer to fit in that blank. All right, here's a little bit harder. Write a nuclear equation for the following statement. Iron 59 emits a beta particle to form cobalt 59. So the symbol for iron is Fe. And we know there's iron 59. When we're writing it like that, that 59 refers to the mass number. So if you go look on the periodic table, go find how many protons are in iron. You should find 26. You need to practice it. When I say go look at the periodic table, go look at the periodic table. Okay, yields. We know we're making a beta particle. Well, we'll just leave that off for a second. And cobalt 59. So cobalt is abbreviated CO. And we know it's 59. So that's our mass number. If you go look on the periodic table, you should get 27 for our number of protons. So now we're emitting a beta particle. If you remember, you can look it up, but sometimes You just get a little stuck. So I know a beta particle is an electron, so I'm going to put an E. If I have 26 protons on this side and 27 on that side, what has to happen? I have to have a -1 there. If I have 59 here and 59 here, I have to have a 0 here because they have to equal. Okay? So if you remembered, you could have thought to yourself, okay, a beta particle. I know a beta particle, right? One neutron becomes a proton, right? So that changes my number of protons. I lose a proton, so it's a -1, right? And you emit a high energy electron, but that electron has no mass, okay? All right, so let's do a few of these. We're not gonna do all of these, but let's do a few of these. All right, so write a balanced nuclear equation for the decay of each of the following. Carbon-14 undergoing beta decay. All right, so let's see if I just do this. If we have carbon-14, so I'm saying carbon, and that's telling me my mass number. I go to my periodic table. I know carbon has 6 protons, and it's undergoing beta decay. I could remember what a beta particle is, or, well, no, for this one, yes, you actually have to do remember, because that's the only thing I tell you, beta decay. So I'm going to say it's an electron, and I know a neutron becomes a proton, so we're going to lose a proton, and it has no mass because it's just emitting that electron. Okay, so I know that this number, if I look here, my number of protons must equal on either side. So in order to make that equal, I need to have a 7. 7 minus 1 is 6, so I'm good. So then I go on the periodic table. What has 7 protons? And that is nitrogen. And so if we know our mass number before, and all we did was add another proton, we still have nitrogen 14, right? Because we know, let's see here, our mass numbers have to equal. And we know, in fact, that they do. So that's good. Okay, B. What do we have? Polonium-212 undergoes alpha decay. Polonium is PO. And so we have 212 is our mass number. Go look on the periodic table. Polonium is 84. And we're going to undergo alpha decay. Alpha decay, remember, is a helium atom with 2 protons and 2 neutrons for a mass number of 4. Now, what's going to happen? So let's look at our mass number first, right? How are we going to make these two sides equal? So I'm going to have to take 212, subtract 4. I get 208 for a mass number. Then let's look at our number of protons. How are we going to make that equal? So I'm going to need 84 minus 2 is going to give me 82. So now that I know that I have 82 protons, I can go look on the periodic table and find out which element has 82 protons. And when you do that, you should find that that is lead, Pb. Okay, let's try another one. Let's try C. Copper-66 undergoing beta decay. All right, so copper is undergoing 66, is undergoing beta decay. So beta decay, we are going for an electron, right? We're going to lose our proton and give it a 0, right? And we need to go look on the periodic table, and we need to figure out which element, not which element, copper has how many? Copper has, I didn't do this one, 29, right? Okay, and so what do we have to do to make those sides equal? This one is going to have 30. So if you look on the periodic table, which one has 30? That is zinc, Zn, right? And now we have to make our mass numbers equal. So 66 minus 0, 66, right? Okay, one more, last one. Let's do D. Let's do D over here. I'm running out of room. I'm always running out of room. All right, Californium. Probably never done anything with Californium before, CF, right? 251 undergoes alpha decay. So alpha decay, remember, that's your He, 4 and a 2. All right, so Californium, go on the periodic table where you find it down there in those elements that are beneath the normal part of the periodic table, so those intertransition metals, and you'll find that it is number 98. So then you're going to produce something, right? 98 minus 2 is going to give me 96, right? And then my mass number, 251 minus 4, 247. And so go look on the periodic table and find which element, and that is Cm, okay? And I think that's it for, oh, no, we have one more. Okay. Write a balanced nuclear equation for the beta decay of cobalt-60 used in brachiotherapy. Okay, so what do we have? Cobalt-60, CO, we have 60 here. We're going to go look on the periodic table, find cobalt, and we're going to find that cobalt has 27 protons, and it's undergoing beta decay. So beta decay, I know that I'm losing that proton. That proton gets converted to a neutron, right? So our mass didn't change just because we converted a proton to a neutron, because protons and neutrons have the same mass. And we're going to produce something new. Okay, so 28 minus 1 gives me 27. That's what I want. All right, and then my mass number has no change, so that's still 60. So I just need to go check the periodic table. What element has 28 protons? And that should be nickel. Okay, that's it. All right. See if I can stop. Oh, I think I stopped the share, but not the recording. Oh, technology, man, technology. Okay, let me see if I can stop this.